Welcome to week 3, everyone. Hopefully that foam demonstration was helpful for you as we continue our discussion of structural analysis this week with perpendicular forces. I do apologize if the video seemed a bit wobbly toward the end, but I don't actually have a digital camera or a tripod, so I had to get a little creative, and I'll put up a picture here to show you what I'm talking about. Yep, that right there is what we'll call engineering ingenuity, I guess. Anyway, I'd like to take a step back for just a moment before we continue any further by talking about boundary conditions, or end conditions as we called them in our buckling equation. And this should be review from Structures 1, but I wanted to give you a brief refresher of what these different symbols actually mean and provide you with some real-world examples. Note that we are only discussing 2D structural analysis in this course. We'll leave the 3D calculations to the structural engineers. So let's start with a roller. A roller provides only one reaction in one direction. It does not provide any restraint against lateral translation or rotation. So if we looked at its response to loading here, it would look like this. There would be no change in the vertical position of the member at the location of the roller. However, the roller will allow the member to translate horizontally as well as rotate freely. And so we only have one reaction in the vertical direction, or we can also turn the roller on its side, like this. And in this case, the roller only provides restraint against lateral translation. Next, we have a pin. Similar to a roller, a pin allows the member to rotate freely. However, in addition to providing a vertical reaction, a pin now also offers restraint against lateral translation. Lastly, we have our fixed condition, and here we have restraint against all three types of movement. We have restraint in the vertical direction, restraint in the horizontal direction, and restraint against rotation at the end of the member. And so you can see in this response to loading diagram, at the location of the fixity, the member will remain at 90 degrees. We can also talk about these end conditions in terms of joints between two members. In the case of a pinned joint, if we were to load this horizontal member, it would be free to rotate about the joint. However, the vertical and the horizontal forces would translate through the joint and into the perpendicular member. Lastly, we have a rigid joint. Like the pin joint, we are passing our vertical and horizontal forces from one member to the other. In addition, we are also passing rotation from one member to the other. And so the angle between the two members remains at 90 degrees. Now let's take a look at some real-world examples of these different end conditions. And let's start with rollers. So this hanger here would be considered a roller. We are providing a vertical reaction to support the weight of this pipe. However, we are not providing any restraint in the x direction along the member. And so we would draw that like this, with this blue line representing the pipe. The reason we often use rollers for pipe supports is because pipes are often made of some type of metal. And metal, of course, as it heats up and cools down, will expand and contract. And so there will be some elongation along the x-axis direction. And as we learned in week 1, if we restrain that change in length, we will create forces or stresses in the pipe. So instead, we want this pipe to be able to change length freely without restraint and roll over the top of this support. Our next roller condition is precast concrete. And precast, of course, means that these concrete pieces are cast or formed somewhere else off-site and brought onto the site as big pieces, kind of like building blocks. And often these pieces are wide enough and massive enough that we can simply rest one piece on top of the other without providing much restraint, and the total structure will still remain stable. So what is often in the case with parking garages, we will lay this precast concrete beam on top of this concrete corbel without any real rigid connection between the two pieces. And so in this case, we would also refer to this condition as a roller support. Now let's move on to pin connections. And the first type of pin connection we're going to talk about is a steel pinned connection. So when you look at a steel connection, if you see that only the webs of the supported member are connected to the supporting member, in this case this column, then we know that this is a pin connection. And you can see here in this photo that there is daylight between the flanges of the supported member and the column. So only the web is connected to the supporting column. Therefore, we will only be passing a vertical force from the beam into the column, as well as any horizontal or axial forces that we may have in these beams. But we will not be passing any moment from our supported beam to our supporting column with this type of connection. Similarly, with a joist seat, we will pass our vertical force from our joist into this supporting beam here, as well as any horizontal or axial force in the top chord of this joist. And so we will have a reaction here and a reaction like this. Note that the bottom chord is not connected to the supporting beam. Also note that most wood connections are pinned connections. It is very difficult to achieve a fixed connection with wood. Also, if we take a look at our precast again, however, this time we have two steel plates connected to these precast members, and we are applying a weld between the two. Now we can call this a pinned connection, where we can pass a vertical force into the supporting column, as well as an axial force. Lastly, let's look at a base plate example. And a base plate is what we will have between a column and a pier, which is a foundation element, which we will discuss later in this course. So if we have a base plate that has bolts only located between the flanges of the column, then this will be a pinned support. We will be able to pass our vertical reaction into the foundation, as well as any horizontal force. However, we won't be able to pass any moment that there happens to be at the base of this column. Now let's move on to fixed connections. And we'll start with a steel connection from a beam to a column, as we saw earlier. But now, note that we are welding the top flange and the bottom flange to our supporting member. And note that this supporting member could be a column or a beam. In this condition, now that we have provided a connection between the flanges to the supporting member, now we can pass a moment from our supported beam into our supporting column. So a fixed connection requires that we attach, either by welding or bolting, both the top and bottom flange of our member to our supporting member. Our next fixed condition is cast-in-place concrete. Cast-in-place concrete is of course cast monolithically, meaning that this entire member is cast as one piece, both column and beam. And so of course, any bending that occurs in the beam will pass into the column. Finally, let's look at some real examples of pinned and fixed joints. Pinned joints are what you will often find in typical steel and wood framing. So the connection between a steel or wood beam to a steel or wood column will typically be pinned. Also, the joints between truss elements and arch elements will also be pinned. Finally, the joints between all of the elements of a steel braced frame, including the brace itself, all of those joints will also be pinned. There will be no restraint against rotation at any of these joints. With fixed joints, of course, the obvious example is a moment frame. Moment frames and brace frames we will be talking about more in depth later in the course. Trusses and arches we will be discussing next week. For this week, we will be focusing only on beams. And our next topic will be how to solve for reactions at either end of a beam.